more through our networks. With Inel, your Have you ever wondered what benefits you get from being an Inel student? Your learning will not only remain in theory, you will also learn through practical cases, software, projects, and more. You will share experiences and knowledge with students from various countries and receive continuous advice from high-level instructors. In addition, you will have access to the virtual platform where you will find resources and complementary material, so you can be able to relive the classes whenever you want. Don't forget that our certifications are internationally recognized. Get to know us a little more through our networks. With Inel, your education has no borders. Have you ever wondered what benefits you get from being an Inel student? Your learning will not only remain in theory, you will also learn through practical cases, software, projects, and more. You will share experiences and knowledge with students from various countries and receive continuous advice from high-level instructors. In addition, you will have access to the virtual platform where you will find resources and complementary material, so you can be able to relive the classes whenever you want. Don't forget that our certifications are internationally recognized. Get to know us a little more through our networks. With Inel, your education has no borders. Have you ever wondered what benefits you get from being an Inel student? Your learning will not only remain in theory, you will also learn through practical cases, software, projects, and more. You will share experiences and knowledge with students from various countries and receive continuous advice from high-level instructors. In addition, you will have access to the virtual platform where you will find resources and complementary material, so you can be able to relive the classes whenever you want. Don't forget that our certifications are internationally recognized. Get to know us a little more through our networks. With Inel, your education has no borders. Have you ever wondered what benefits you get from being an Inel student? Your learning will not only remain in theory, you will also learn through practical cases, software, projects, and more. You will share experiences and knowledge with students from various countries and receive continuous advice from high-level instructors. In addition, you will have access to the virtual platform where you will find resources and complementary material, so you can be able to relive the classes whenever you want. Don't forget that our certifications are internationally recognized. Get to know us a little more through our networks. With Inel, your education has no borders. Have you ever wondered what benefits you get from being an Inel student? Your learning will not only remain in theory, you will also learn through practical cases, software, projects, and more. You will share experiences and knowledge with students from various countries and receive continuous advice from high-level instructors. In addition, you will have access to the virtual platform where you will find resources and complementary material, so you can be able to relive the classes whenever you want. Don't forget that our certifications are internationally recognized. Get to know us a little more through our networks. With Inel, your education has no borders. Have you ever wondered what benefits you get from being an Inel student? Your learning will not only remain in theory, you will also learn through practical cases, software, projects, and more. You will share experiences and knowledge with students from various countries and receive continuous advice from high-level instructors. In addition, you will have access to the virtual platform where you will find resources and complementary material, so you can be able to relive the classes whenever you want. Don't forget that our certifications are internationally recognized. Get to know us a little more through our networks. With Inel, your education has no borders.
Good morning, dear participants. Welcome to Inel and our new cycle of masterclass. Who is greeting you is Fabricio Cárdenas, your tutor. Today we are going to talk about real application case of transmission line protections in PowerFactory. This is the QR that during the presentation of our instructor, you will have access to the consultations form. There you can make your questions according to the topic presented. This is our commercial executive, Lisbeth Are. You have her contacts here in the slide if you have any doubt, or you need more information about programs in Inel. I present you our new instructor, the Master of Science Muzamil Faiz, who is an specialist in power system protection, engineering and electrical power by Mehran University of Engineering and Technology, Pakistan, with an executive MBA in finance by University of Sialkot, Pakistan. A specialist with more than 14 years of work experience of power system planning, analysis, maintenance, and management. preparation of electrical studies of the power system. Currently instructor of Inel Escuela Técnica de Ingeniería and lead engineering HV power system at ARUP, London. He has experience in protection of power systems, advanced experience in power system, and realized testing, equipment, and installation from world's leading manufacturers, protection, setting, calculation. Now I will leave you with him, who has a big presentation for you. Good morning, Mr. Muzamil. You now are able to share your screen.
Thank you. Good morning, everyone. Can you please confirm me that now you are seeing my screen?
And yes, your screen is.
So thank you so much. As our presenter has described, that now we are going to discuss a real case of transmission line protection. As you are all.
Sorry to interrupt you, Mr. Muzamil, your camera is off.
Camera is off. Oh, sorry.
Yeah,
okay.
Now it's good.
Thank you. All of us, I think, well aware of the fact that transmission lines are carrying out the power from generating station to the load areas, as we believe that the generating stations are located at mainly on odd locations. Like if there is a hydropower potential, it is mainly located in hilly areas, and if there is a coal potential, then it is located in far-flung areas. So from those high potential areas, carrying of power from those generating station to the load areas, there is a need of transmission lines, and so these are the actual backbone of the power system, which are connecting the generating station to the actual end side consumers. So protection of these transmission lines, therefore, of much importance, and there is no such a right segregation of the transmission lines. So it is mainly depends upon the utility in which you are actually dealing. As far as IEEE and IEC standards are considered, we can say that if there is a 34.5 kV power and the lower, then it is considered as industrial distribution network. But if power is between 34.5 kV to 138 kV level, then we can say that this is sub-transmission level. And if power is above 115 kV, then sometimes we call it as transmission level. As you can see that there is 138 kV, which is considered as sub-transmission, but at the same time, 115 kV is considered a transmission line. So there is no clear-cut boundary between the transmission line and sub-transmission line. So we may consider like the transmission and sub-transmission as one entity, and the distribution, which is up to the 34.5 kV level, this is something we can say that this is distribution level. So this is classification of the transmission lines. There is another classification which we usually have in books, like if the transmission line is less than 80 kilometers, then it is considered as the short transmission line. If it is between 80 and 250 kilometers, then we can say it as a medium transmission line. And if it is greater than 250, then we are usually considering it as a long transmission line. So there is two types of distribution or classification of transmission lines. Like one is on the basis of their length, and other is on the basis of their voltage level on which they are actually operating. So today we will discuss main features, like how we will protect these transmission lines. In power system, the main concept of protection is depending upon the importance of the system. Like if the system is carrying only 1 megawatt of the load, then it is not that much important. because the power system which we are actually operating is in the level of gigawatt. So if the capacity is 1 megawatt, so it is not that much important for us. But when we are talking about the transmission lines, so they are actually carrying the bulk power from one station to another, point A to point B. That's why these high power capacity of the transmission line make them more important. So we need to focus on them. Like if one transmission line trips for no reason, then it means that the at least 10,000 people at least, which is the minimum value, will be affected, and maybe many substations will also be going to the brownout condition. And if the cascading occurs, then we may be involved into the blackout conditions. And what are the objective of the protection system? So basically, we are protecting it to minimize the disturbance, to protect our equipment connected with that transmission lines. Like if there is a fault on the transmission line, and we have a heavy equipment connected on both sides of the transmission line. Like if transmission line is connecting generating stations to the load center, then on the both end of the transmission line, there will be very much costly equipment connected. So we need to protect on both sides of the transmission line. Like on the one side, there is a generators, then transformers, and on the substation or station side, there is also a very much costly equipment. So we need to protect that equipment, and also we need to maintain the stability of the power system, which makes the protection of transmission line much more important than any other equipment. Like even transformers are important for us, but for one transmission lines may be energizing multiple transformers. So if one transformer goes out, transmission line will keep working. But if one transmission line goes out, then maybe multiple transformers will be out of the operation. That's why it is important to protect the transmission line, and it is also enhancing the transient stability of the system. And first of all, we can't stop the faults. We only can protect the equipment connected. So if there is a fault, then we need to open only those breakers which are mainly affected. We can say this property like this is a selectivity option of the protection system. Like it must be selective in nature. In other words, we can say that if there is a fault between point A and B, then the outage should be only in this region A and B, not on the side of the C or D or something like that. So it should be selective in nature. It should know that where the fault is actually happening and what portion of the network it needs to be protect, and also to keep de-energized. And as we also have discussed that transmission lines are of much important to us, to our system stability. That's why we need to re-energize the transmission lines much faster than any other equipment, because a heavy load is flowing through the transmission line. If it is interrupted, then there may be some cascading operation, and we may have some brownout or blackout condition. That's why there is a auto recloser option which transmission lines should have, and these are implemented during the protection system. So overhead lines should be re-energized automatically, which is the auto reclosing option. And also protection system should not be so much sensitive that it will operate when the transmission line is operating near or on the on its thermal stability limits. So it should know that which amount, which magnitude of the current is a fault and which magnitude of the current is a overloading condition or heavily loading condition of the transmission lines. So these are basic objective for the transmission line protection, which we need to consider. When we will discuss the protection calculations and also the implementation, then I'll explain it a bit more. Now, there is another classification of lines, which is actually on the basis of source impedance ratio, which is more concerned about the we can say that about the location of the relay and also the fault level which is available at the station where we are going to connect our relay for protecting a transmission line. Generally, there is a source to line ratio. Impedance means source impedance to line impedance ratio. If it is greater than 4, then we can say that it is a short transmission line. Let me show you. And other is source impedance ratio. If it is less than 0.5, then we can consider it as a long line. And if it is between like 0.5 and 4, then we can consider it as a medium transmission line. This is the same kind of classification which we have, like if the transmission line length is 80 kilometers or less than 80 kilometers, then we can consider it as a short line. And if it is between 80 and 250 kilometers, then it is a medium line. And if it is greater than 250 kilometers, then it is a long line. But for the power system protection, we classify them on the basis of this source impedance to line impedance ratio. So this is source impedance and line impedance ratio. And next, why we protect the transmission lines, like why it is needed to protect the transmission line. We already have discussed that, but we need to maintain the stability of the system. That's why we have to protect the transmission lines. We have to avoid the unnecessary outages which may be caused. One reason may be the fault, and other reason is the mal-operation of the equipment connected. So we need to keep an eye on the network operation. Like if it is a fault of the permanent nature, then there should be a disconnection of that transmission line. But if the fault is a temporary in nature, then there should be a auto reclosing operation. Like if transmission line is out on the temporary fault, then after some time we need to reclose it automatically. And if there is a mal-operation, then a relay should be intelligent to discriminate between abnormal operating conditions and the normal overloading conditions. So these are actually distance protection features which we need to set in the relays. So this is main reason why we are actually protecting the transmission lines. And next, how we protect the transmission lines. Like everything, we have some basic rules, some basic assumptions, how we will protect these equipment. In the transmission line, like distance protection, we have a comparator which is actually taking two quantities like voltage and current at a location. And you also know that there is a calculation which, if we divide the voltage with the current, then the quantity which we get is the impedance. So when the transmission line is fixed, like it is 100 kilometer, then its impedance is fixed at the moment when we decide that what would be its length. So now we have one quantity which is impedance of the line, and we have another quantity which is impedance measured during the operation. So we have two quantities, one which is fixed quantity. It depends upon the construction of the conductor. When we have decided like this conductor will be say this conductor will be a cuckoo conductor and length will be 100 kilometers, then by these two quantities we will have an impedance of that transmission line. But now there is another quantity which will be operating quantity. If at point A, say at this point, we are going to connect a relay, then voltage at this point and current at this point will decide the impedance of this transmission line. So if that measured impedance is greater than that transmission line impedance, then this is a normal operation for the transmission line. But if this measured impedance is less than this actual impedance of the transmission line, then relay will consider it as a fault. And by this comparison, by this amplitude comparison, relay will decide the whether it is a fault or it is a abnormal operating condition or overloading condition. So this is basically a concept of the amplitude comparator. We'll compare two quantities, one actual impedance, which is we will put values in the relay, and then there is an operational impedance which relay will be calculating every moment. There is a current and voltage on the transmission line, and it will compare. And on the basis of this comparison, it will make some decisions. There may be some conditions which we will discuss later, that whether if impedance is less than that value, but still there is no fault. There are some situations, but these are exceptions. We will discuss later. Now, as we have described that there are multiple transmission lines, multiple characteristic, like one is with the SIR greater than 4, with SIR less than 0.5, and with SIR 0.5, between 0.5 or 4. So these classifications are not just to classify the lines, but to protect the lines accordingly. These transmission characteristics, we need to protect them differently depending upon the ground conditions. So first of all, there is a very simple characteristic which any of the relay will have. This is impedance relay, which actually we have Rx plane. We put R on the x-axis, we put reactance on the y-axis, and there is a circle whose center is the, like this one. This is impedance characteristic of the transmission line. So this is R plane, this is X plane, and this circle is actually impedance of the relay, which is characteristic of the relay. Now, from this point to this point, this is the resistance of the transmission line, and on y-axis, this is the reactance of the transmission line. Like we have R plus JX. So this is R and plus JX. Depends like what is the value of X for a typical line and what is the value of R. So the characteristic of the line will be located like on this semicircle of this impedance characteristic. So this is basic, which was on the initial stages of the transmission protection. This is the among the, I think, pioneer characteristics which were used for the protection system. And when we will use, like, this is non-directional in nature. Like if transmission line is from this point to this point, but this is the transmission line from in the back side of the transmission line. Like if this is from point A to point B, so this will be point A to point C. It is unnecessarily protecting the other equipment, and the time of operation of this side and this side is same. That's why this is not preferred impedance characteristic, but initially that was used for the protection of line. But with the advanced research, now better options are there, which we will discuss one by one. The second one option is reactance relay. Reactance relay is its value is increasing in the x direction. Like this is x. Now it is constant y-axis, but its x-axis is changing. Like this is typically preferred for those lines which are short in nature, because if line is short, then its R value will also be small. And if R value is small, then if there is a arc produced during the fault, which is basically, I think everyone knows that when there is a fault, when there is a energization or de-energization, there will be an arc produced, and that arc has a resistance value. If there is a very small length of line, then the circle will become very much small. And if R value increases beyond this point, at this location, say at this location there is an R, then this fault will not be detected by this circle, because what we have learned previously, like if our impedance is greater than this circle, then this relay will not operate. But if the impedance is falling inside this circle, then this relay will operate. And if there is a fault at this location, but due to resistance, the characteristic move from this location to this location, then this will be not detected by the transmission relay. So to avoid this resistance issue, this characteristic is used, which is independent of the R values. It only depends upon the X value. We select a X value for that transmission line, whatever it is, like it's if its length is say 5 kilometers, then as per 5 kilometers, we will set its X value, but it has an infinite resistance value, which will tackle the arc resistance, and also there is, if there is any fault resistance other than the arc. And now the mostly used characteristic of the relay is MOHO, which is admittance relay. Admittance, like if we divide the impedance of a relay, like 1 over Z is equal to Y. So this is called the admittance relay. And this has some direction in nature. Like if we can say that this impedance characteristic, which is equally on the right side and left side, which is non-directional in nature. It doesn't depend upon that if fault is on the front side of the line or on the back side of the line. It will operate with the preset time, whatever direction of the fault is. But this drawback is settled in this MOHO relay or admittance relay. So it has inherent directional characteristic, which is used in detection of fault only one direction. If the fault is on the back side of the line, then it will not detect it, but it will wait for the other relay to operate. And this characteristic is ideal for those lines which are actually longer in length, heavily loaded. So MOHO relay, let me show you this one. This is the MOHO relay characteristic. This has directional feature, like now it is starting from the origin of that are explained. Now it is not seeing on the left side of the this plane are explained. Like this one, this was equally on the right side and equally on the left side, but this has that directional feature. It is only seeing on the forward direction of the line. And now due to this one, it has another feature, which is very much, I think, beauty of this characteristic. Its reach is depending upon the angle. Like at that angle, length of this line or the reach of this relay will be smaller. But if length is increased, like if angle is increased, then its length, then its reach will also be increasing. So this is dynamic in nature. If fault occurs at this angle, then its reach is this one. But if fault occurs at this angle, then its reach will automatically getting increased. So this is Moho relay. It also has some drawbacks which were later tackled by this offset Moho relay. Like what happens if there is a transmission line, say this is a transmission line and our relay is at that ABC location. If fault occurs at this ABC location, what will happen? Because it is seeing from this ABC to XYZ. But if fault occurs at this location, this characteristic will be unable to detect it, because it is starting it from that exact point where fault is occurring, and now it will be, I think, a relay will be in doubt that whether this fault is within zone or out of the zone. So to avoid this issue, there is another characteristic which is offset Moho. Now it is a bit offsetted from this origin, and due to this portion of the curve, this characteristic, now if the fault occurs at this bus bar location, then this relay can be sure about the location and will consider it as a in-zone fault and protect that equipment from the fault, and will operate as soon as we have settled its time. So this is offset Moho, this is Moho. There is a little bit difference between these two, and hopefully you got my point, what I'm there making. Like what are the benefits of Moho relay and what are the benefits of offset Moho relay. Basically, you need to consider this is mostly used characteristic, like the relays with the Siemens, relays with the SCL, relays with Micom Schneider. These all are using such kind of characteristic for protecting the transmission lines. Now there is another which is a quadrilateral characteristic, and this type of characteristic have freedom in setting your R values as well as your X values. Like in this reactance relay, the resistance reach was infinite. It was going in this side and also in this side, and it was non-directional in nature because it was detecting faults on both sides of the transmission line, on the right side and also on the left side. To overcome this issue, there is a characteristic which is called the quadrilateral relay characteristic, and this is basically used on the heavily loaded lines, and also the lines which have short, or I think which we can say that if the there is a source connected with that transmission line which is weak in nature, then this characteristic will be used. And what we mean by weak in nature is like if the fault current at a location is less than a pre-described value, then we consider it as a weak source. So as we have discussed, and now this is also effective when there is a fault resistance, when the lines are heavily loaded, and also when there is a area which is having a high arc fault ratio. So how it looks like, this is the quadrilateral relay characteristic. In this, we have freedom to select. This is R1, which is the uh, resistance reach of zone 1, and this is the X1, which is reactance reach of zone 1. Similarly, R2, X2, and R3, X3. These are looking in the forward direction, and this is a zone 5, which is actually looking in the reverse direction. This will protect the your bus bar and also a portion of bus bar towards substation. There is another characteristic which is lens characteristic, and this is also used in heavily loaded lines. Why it is used in heavily loaded lines? Like if the impedance of highly loaded line is located at this location, at this point, say at this point, and if I'm using a Moho characteristic, then this circle will, I think, will keep this uh, impedance of the line, which is operational impedance of the line, inside that circle, and relay will operate without any reason. It will consider this heavily loaded line as a fault condition and operate, which is not necessary in this condition if the line is heavily loaded. So to avoid that condition, when line is heavily loaded, then we have curved that portion of the Boho relay and make it as a lens relay. Let me show you that one. This is like if the due to heavily loading, if the impedance of the line comes at this location, then this Moho relay will get operated. But now we are taking this portion out and making this impedance of the line during operation comes at this location, then there will be no mal operation of the relay. So this is lens characteristic, which is used for those lines which have high power flow and heavily loaded. Now there is a example how we will calculate the relay settings for a transmission line, and after that we will implement it in the 𝗠𝗥𝗖𝗟𝗏 PowerFactory, and I'll show you how your relay should behave during different conditions. We will apply some faults, and then we will check that whether it should operate and whether it should not. Up to this point, if there is any question, let me know.
Excuse me, Mr. Muzamil, the questions will be after the session, the meeting. I leave the link if they have any doubt.
Okay, thank you. So now we'll taking a example of a typical transmission line, which is 100 kilometers in length, and this is a generating station. This is bus bar ABC, which is at the 230 kV level, and this 100-kilometer line is ranging from point ABC to point XYZ. Now we need to calculate settings. So this is the source impedance, which is 5000 MVA max at this point. And this source impedance means like this is short circuit level at this point ABC. During the maximum fault level condition, 5000 MVA will be there, and during the minimum fault level condition, 2000 MVA will be there. Now we have source impedance. Now this is line impedance. Line impedance is described by the R plus JX values. Like this is Z1, which is positive sequence impedance, and its resistance per kilometer, which is per kilometer is 0.089, and its reactance is 0.476. This is ohm per kilometer. So if this is per kilometer and line is 100 kilometer, we need to calculate it for 100 kilometers. So we will multiply this one, Z1, and also for the zero sequence values, these are the zero sequence values. Normally the positive sequence and zero sequence values are like 3 times of the positive sequence values. If the values are not available, then this is a good engineering estimation, so we can consider it. But for now we are using this zero sequence impedance values 0.426 and 1.576. So this is a typical example. How we will calculate? So this is a basic principle for the calculation of the network settings. We will set 3 zones which will be forward looking zones. Zone 1 will be from point ABC to XYZ, but not exactly up to the XYZ. It will be up to maximum up to 85% of ABC to XYZ. Like this is a 100 kilometer, then this zone 1 reach will be up to maximum 85 kilometer. So from point ABC to 85 kilometer, this will be our zone 1. Then this zone 2 will be from point ABC to 50% of this XYZ, like complete 100 kilometer plus 50% of this XYZ to PQR line. And this will be 50%, like this will be 30 kilometer section. So zone 2 reach will be 100 kilometer plus 30 kilometers. So total 130 kilometers we will be protecting through zone 2. And zone 3, there are different approaches. Like we need to check whether the if there are multiple lines, like in this typical case we are taking only one line, but if there are multiple lines from this XYZ terminal, this bus bar, then we need to consider another approach. But for this typical case we are taking this one. So this is line impedance. We are multiplying it with the 100, and these are the values after multiplication. And now this is conversion from our RX values to impedance and angle values. So this is line angle. This is called line angle, and this is basically calculated by the tan of theta, which will be tan inverse 47.6 divided by 8.9. So this angle will be there, and this 48.42 is basically calculated by r square x square square root, all of the square root. So this is our impedance of the line, and we will consider the near value of the line. Like if this is a 79, or even if this is a 78, we can consider it as a 80-degree angle. There is another thing which is called the residual compensation, and this comes into action when there is a earth fault on the transmission lines. Because when the fault is on the phase conductors, then their parameters are fixed. But when there is inclusion of line, like one phase to ground fault, 2 phase to ground fault, then when there is a ground in the calculation, then we don't have the exact values. But as per the calculations, we can add this residual compensation factor, which will give us the exact values. And we will because in the transmission line, the main factor which is I think need to be considered is whenever there is a fault, we should be, after the fault clearing, we should be going at that exact point where fault has happened. Because if the 100-kilometer line is there, if we are going to patrol the exact 100-kilometer line, then you can imagine that how much time you will take to patrol that 100-kilometer line. If the relay will tell you that the fault is exactly at 35 kilometer, then you can easily locate that fault, and you will be able to rectify it without any further delay. So these factors are considered when there is a uh, any fault which is unsymmetrical fault, single line to ground or two line to ground fault. And its calculation mechanism is like zero sequence impedance minus positive sequence impedance and divided by 3 multiplied by positive sequence impedance. And we'll take the absolute value, and this will be magnitude of that compensation factor. And by this value, we can calculate the angle of that compensation factor. So basically, it depends upon the a parameter of the conductor connected, like this one. These values are there. If this conductor is with these parameters and this conductor is with some other parameters, like this is 0.89, but this 60 kilometer is not with the 0.89, this is with the 0.69, then we need to calculate for this one and then add these values. So there will be a different approach when the conductors have different parameters, but for that typical case we are using the same values. That's why it is easy to calculate. But if there are multiple lines, then there will be a Z0 1 plus Z0 2 minus Z1 1 minus Z0 2. So this will be calculated by this way. So final values are 0.792 and the angle is minus 6.5, and these will be this will be considered when there is a ground fault. Now we are going to calculate the phase reach of the relay for the zone 1. For this typical case, we are using the 80% reach, which is 48.2, which is total line length with the angle, and I am multiplying it with 0.8, and this value is 38.74 with the same angle, because multiplying it will not change the angle magnitude. So we'll use any nearest value available. Like if 38.74 value is not available in the relay, because relay has some minimum values which can change. Like if they are changing the 0.1 value, then you may have only 38.8 value. But if they changing 0.1, not necessary to exactly 774. You may use 75 or you may use the 80. So for the zone 2, there are two approaches. One is we can use the 120% of the protected line, or if there are multiple lines, then we need to consider that protected line length plus 50% of the next shortest line. Like if I'm going there, this point, this is 100 kilometer, and if I'm taking 120% of this protected line, then this will totally be equal to 120 kilometer, because I'll be multiplying 1.2 with this 100 kilometers, so it will be 120 kilometer. And with the second approach, the complete protected line plus 50% of the next line. So in this case, our setting values will be 100 kilometer of this and 50% of this, which will be 30 kilometers. So in this case, it will be protecting the 130 kilometer, and with the other approach, with this value, it will be protecting 120 kilometer, and with this approach, it will be protecting 130 kilometer. So we need to check, because protection system is not a science. Like every time we will be multiplying this with the 120% value, and every time we need to multiply it with the 50% value of the next line. We need to check from case to case that which value will suit our network conditions. And this is the zone 3. And there are multiple approaches to calculate zone 3 also, as with the zone 2. One approach is to consider the 120% of the sum of the lines between substation ABC and PQR. like this one, 100 kilometer plus 60 kilometer. So total will be 160 kilometer and 120% of this one. So we will multiply 1.2 with that 160 kilometer. And uh, this is one approach. Another will be 100% of this line and 120% of only this 60-kilometer line. So in this case, it will be protecting like 10% and 12, 72. So in this case, if I'm taking 120% of only this portion, 60-kilometer of line, it will be protecting 172 kilometer, which will be at this location. Why we are using this zone-based approach? This is because we need main protection. Main protection will be for this line section. And we also need backup protection. Like if the relay at this location, which is for the XYZ, got failed to operate, then we should have a backup protection from this ABC side. And after some time, which is pre-decided in our case, it will be 300 millisecond. If this relay is not getting operated, or there is a stuck breaker condition at this point, then after 300 millisecond, this ABC relay will provide backup protection for this section of the line. So it will isolate the faulty portion also. That's why we are using this relay is protecting with the zone 1, this line section 85%. With the zone 2, it is 120 or 135% of the next line. So it is protecting the whole of this main line and some portion of this. But it should have some delay, because if fault is at this location, then this portion should be isolated by this relay, not by this relay. So zone 2 will have 300 millisecond time and zone 3 will have 700 millisecond time. For this relay, its prime responsibility is this section of the line. For this relay, this line is prime responsibility, and this relay will backup protection to this PQR section. And this ABC relay will give backup protection to this portion and also this portion. So this is zone 3 setting, and we have calculated it like 83.275 and with the 80-degree angle. And this is the implementation in the PowerFactory. I have modeled this network like this is 60-kilometer section, this is 100-kilometer section, and I have a relay at that ABC point. This is ABC location, this is XYZ, and this is PQR. Now this is relay, and for the distance protection, 2 instrument transformers are necessary. One is current transformer, and this is the current transformer connected at this point, and other one is the voltage transformer or potential transformer. So this is connected on the bus bar. It is taking the voltage from the bus bar, and this is taking the current from the line. And by this V over I ratio, this relay will be measuring impedance through the line. Now we have 2 values: one, fixed impedance of this line, and the second quantity is impedance measured by this relay. And we need to compare these 2 quantities. If the measured impedance is greater than this line impedance, then this is normal condition and relay should not operate. But if the measured impedance is less than this transmission line impedance, in this case, relay will consider as a fault and it will isolate the faulty portion with the pre-decided time. And now this is line section where we have put our data. This is line section ABC to XYZ. And these were the parameters which we have calculated earlier. And for this, like the line impedance is 48.42, and you can verify from this point, like this is 48.42. Our angle was 79.2 6.41, and this is 79.41. And our earth factor magnitude, which we were saying like residual compensation factor, and these are the values 0.79 and minus 6.4, which I have implemented in the PowerFactory. And if you can also check it from this one, this is 0.792 magnitude and minus 6.5 compensation factor angle. So we have implemented this magnitude 0.79 and minus 6.45. So these are values which I have entered in the transmission line section. And then after that, I have some time distance diagram. I have created time distance diagram for this network, like what will be the reach of the first zone, what will be the time of operation of first zone, and similarly for the second and third zone. Now, this is time distance diagram. This time distance diagram you can easily create from the Dixieland PowerFactory, and if you will be with us, then I'll show you how to implement in the PowerFactory. But for now, take it. This is point ABC. This is point XYZ, and this is point PQR. And you can also verify that the length of this section is higher than this one, because this section is 100 kilometer and this section is 60 kilometer. And other one, you can check that this is not covering the 100% of the XYZ portion, ABC to XYZ. This is only taking 80% of that portion. And then this is zone 2, which is actually having, this is an inherent time delay, which is 20 millisecond for the delay. So this is operating without any intentional time delay, zone 1. For zone 2, this is taking 300 millisecond time, and this is zone 3. So you can see that this is 80% of the line. This is 50% of next line, and this section is 220% of. So it is ongoing. It will be in front of that PQR section, and this is time of operation of this section. Now I also have implemented some of the faults. These are the faults, like during normal load flow, you can check that this relay has infinite time delay to operate, which is 999 at this point. So during normal load flow, this relay will be stable one. And now I'm applying a fault, which is zone 1 fault at this location at the 50% of the line, because this zone 1 is up to 80% of the line, and I'm applying a fault at 50% of the line. So this will be a zone 1 fault, and relay will operate without any intentional time delay. So you can check that this relay is getting operated with very much less time, which is I think 20, maximum 20 millisecond time. So this RX characteristic, which is for the MOHO characteristic, we also have discussed this one. So this is zone 1 reach, this is zone 2 reach, and this is zone 3 reach. I have applied a fault which is well within zone 1. So this relay is operating without any intentional time delay. For the zone 2 fault, I'm applying fault at this location, because up to 80% this is zone 1, but after 80% this is zone 2. So I'm applying a fault at this location, which is XYZ bus bar. This relay will consider it as a zone 2 fault, and it will operate after 350 millisecond or 300 millisecond, whatever we have settled there. You can check that this is a fault in the zone 2, and now this is a time delay which is we have settled for the zone 2. Similarly, I'm applying a fault for the zone 3, which is greater than the 50% of this line, and in this case this relay will detect as a zone 3 fault and operate with pre-decided time delay. This is zone 3 fault. Now this fault point, this surge shows that this is not in the zone 1 region, this is not in the zone 2 region, but this is in the third region. So this is time of operation of the relay, zone 3 fault. This is all from my side. Thank you.
Thank you, Mr. Muzamil. Now I will share my screen because we have a free certification for the participants.
Thank you.
Okay, so dear participants, as I said, we have a reward for your effort to be in this masterclass. Inel will give a certificate for your active participation. To get it, you should follow the next steps. First, enter or scan this QR that is shown in the screen. This will open a Google form that you should complete with your information. This certificate will be sent by your email address. Remember that Inel is compromised with your learning. I will leave this a couple of minutes and also I will share the link in the chat, okay? And also, if you have any question or doubt about this masterclass that Mr. Muzamil just done, you can scan this QR or also you can enter by this link that I will share again. And these answers will be given by you in also email in this couple of days. So that will be all. Thank you very much for your attention. Thank you, Mr. Muzamil. That was a good masterclass.
Thank you.